Good afternoon, everybody. Today's Voyages prac, we'll be looking at some techniques for natural language processing using Colab again. And we'll go through not all of the topics that we talked about in this week's lecture, but a few of the more interactive techniques for preparing data, language data, and working with it for doing things like sentiment analysis. So the notes for this week in the Zoom chat, we're going to look at linguistic features, word embeddings, sentiment analysis, and sarcasm detection. We'll talk about some of these in a little bit more detail as we go through. Each of these activities has a Colab attached to it. Then you might find that you prefer to build separate Colabs for some of the different processes that we do within each of these focus areas. You could potentially do all of this within a single Colab, but it might become unwieldy. And there's potential for data leakage if you're not careful with your variable naming. We'll begin with looking at the linguistic features that we can extract using one of the popular NLP libraries these days. It's called Spacey. Not sure if that's how you pronounce it, but it seems like a good way to pronounce something that's written with a capital C near the end of the name. So traditionally, the Python package of choice for doing NLP stuff is called the Natural Language Toolkit, or NLTK, and we'll use that in today's session as well for different techniques. Spacey maybe is a little less feature-rich as NLTK. NLTK is commonly used in research. There's a lot of different ways of doing things, and it comes with corpora. You can download English corpora, different data sets to use in training and developing and testing the NLP techniques that you're working with. Spacey is a bit newer on the scene and has some pretty nice code interfaces to it. So we'll see some different approaches to using Spacey or NLTK. So in our first activity, we're going to break down some language, some sentences, and look at how the tokens that we talked about in the lecture can be tagged with part of speech labels or named entity labels. So when we break some language down, can we understand which parts of the sentence are, say, the nouns or the verbs, the grammatical structure of the sentence, and can we identify people's names in the sentence, organization names, locations, dates, times, things like that. Now, the data that we're working with today is in English. Spacey and NLTK can work with different language data, and it's possible to train systems for languages that are not supported by these programs with more fundamental technologies. For this is quite a beginner kind of session, so we'll work with English language as much because we have the support of these toolkits, and we can possibly more commonly see what's going on in the output of them. So this Colab, get the link to this Colab from the Voyages webpage that I've put in the Zoom chat. Open it up. The first thing to do is to save a copy of it into your Google Drive so that any changes that you make will be saved. So it should be shared with comment permissions enabled, ideally. So feel free to put comments onto this Colab as we go through things, or even later, particularly if you find errors in it, mark them up so that we can come back and address those. Now, the Spacey library takes language data as an input, and it can be used to do a whole lot of different NLP processes. It operates by first tokenizing the language data and then performing different kind of pipeline tasks on it, the data. So we can see in this image, the process of tokenization happens in a few stages. The key ones here, it's interesting to look at in the example, let's and the NY abbreviation. So let's gets split into this let and let form and the suffix, the plural suffix, the ownership suffix, and the NY is broken down. The punctuation is separated from it, but it remains composed as a group of initials. NLTK will do this in a slightly different way. But fundamentally, when we input data into Spatie, or when we load data into Spatie, we'll have this sequence of tokens to operate with rather than a series of strings. So the first thing to do is to install Spatie in the Colab. And you'll see that I'm using this upgrade parameter here. Sometimes the Colab seems to use an older version of Spatie, which doesn't have some of the features that we'll be looking at. So if we run that, the Colab will connect. We can see the status of the connection up on the top right. For the work that we're doing today, we're working with text and we're not doing any massive neural networks. So it's fine to run on a CPU runtime. We don't need to change the runtime type to GPU. So the Spatie installation could take a little moment. You can see it's downloading and installing. If the earlier version of Spatie was already installed, then we'll also see that it's uninstalls that. Sometimes you'll need to restart the Colab after upgrading libraries, and if that's the case, Colab is polite enough to prompt you to do so. Usually you get a notification pop up here in the bottom area of the code output that prompts you to restart. I've got a reminder here as well that after upgrading, you may need to restart the notebook. Now we'll load the data that we're going to work with. So Spatie does have this corpora that we can use. There's this web corpus of English language. There's a small, medium, and large data sets. For this activity, we'll use the small data set, and later activities today, we'll use a large data set. We'll download that separately. So the different data sets have different attributes. The small one is pretty quick to download, and it has sentences in it that we can, sentences and token information that we'll use to process other text that we can put in. So we'll also use this tabulate package to output the results of our NLP techniques. This is at the top of the code cell here is something that we might not have seen before. Percent time. This is a magic keyword which outputs the runtime of this code cell. So you can see when I hover over commands in the Colab, I'll get this pop-up which gives me a definition of what that is. This can be quite handy. Okay, so we start with initializing the time magic, and then we'll import the tabulate Spatie. We'll download the data set, and then we'll load the data set into this NLP. We've run this validation command just to see that we've got Spatie set up properly, and we can see the pipelines that are available to us. So I'll execute this, run this code cell now. So the data has downloaded, and we have some information about where space is installed on the virtual machine, and we get version information. So we're using version 3.1. Here, the pipeline information tells us that we have access to some different NLP tasks taken to vec tagger, a parser. So the tagger is the point of speech tagger, and lematizer, and named entity recognition pipeline component. Now, this output is the result of the time magic keyword. So whenever you start a code cell with this time magic keyword, then you'll get this kind of output at the bottom, which tells us how long it took to run that cell. Now we can process some text by using the spacey tokens. We begin by loading a sentence into this NLP object. The headers is just used to make a pretty table that will output. We'll iterate through the doc that the spacey creates. So when we use some sentences when we use a sentence in spacey, it creates this doc object, and it's a generator of token information. So we'll iterate through the generator, and we can look at the data that's in there. So I'll run this and we'll see what the output is. Then we output the data in this using the tabulate package to make a slightly more human readable output rather than the plain strings that it might otherwise give us. So we can see that that spacey has broken our input sentence down into these tokens. So Dan did not see the turtles in the lakes that day. The interesting breakdown of the didn't into the didn't forms, and the rest of it's pretty straightforward. And then the second column, we have the lemma form of the original tokens, and that's pretty straightforward. The only major change there is that the turtle's plural noun has been resolved to a turtle singular noun. Leo, I'm just going to put the link in the Zoom chat again because you probably didn't get it, and I'm going to drop the assessment criteria sheet for today in the Zoom chat as well. So if you go to that Zoom, follow the link in the Zoom to the Voyages prac 3 NLP page, and we're currently working through, we've just started on this first collab. Let me know in the chat if you want us to wait for you. Pretty much we've just installed the packages and loaded the data. Okay, so the text column is the original tokens. The lemma column is the lemmatization form, lemmatized form. And we see the parts of speech of each of the tokens. And the tag is the part of speech tag that is also used. Just a shorter version. The dep column is the dependency modification, and when we do the dependency parsing in a moment, we'll see those being used. We see a shape information about the tokens, which is kind of cool. It relates to the capitalization or the punctuation shape of the word. And we have a column that says whether it's alphanumeric or alphabetical. And so we'll see a few items in that column have a false value because they include punctuation. And we have this stop column. Now the stop column's quite interesting because it is a representation of like how significant the words are in terms of their meaning. So these, depending on the process, the NLP process that we'll use, if the word or if the token is a stop word, then they can be excluded from the processing if they're considered to be not significant. So we'll see that words like in and the are stop words. Did not, these are stop words. They're not likely to be significant for working out concepts like meaning in a sentence. Okay, so that should be fairly straightforward. How has everyone been able to generate that table? Any questions about these forms? So then we can use these tokens. So a lot of this information we've just sort of presented it here for the sake of having a look at the data structure that Spacey creates for the tokens. So these are all attributes that we can access if we need to. And we'll do that again with a different sentence. And feel free to alter these strings, these sentences as you go through it. So you kind of play with the input sentences and rerun the cells, see how it changes the output. So we'll use a slightly different sentence here. And what we'll look at now, we'll have the token.text. So that's the same as what we saw in the previous example. Token text. Now, instead of looking at the lemma form, we'll have a look at the morphology of the word. We'll get the dependency again. And now that we're doing the dependency, we also want to look at the head words that are related to each token. Part of speech tag for the head word, and then we can also look in token.children for child words for each of the tokens. So there's a list there of what those things mean. We'll run that. So the text column, same as we've seen before. This is new information here, the morphology. So this gives us a breakdown of the morphology of the words. Past tense, singular. And we have this dependency information again. The head text column tells us what the dependency from each word is to other words in the sentence. And it's kind of, you can work out the relationships reasonably well by looking at that column. And then we can see the children of each of the head words. So where a word has children, that means it's a head word. We can see that saw has these children, it also has this child. So it can become more complex, especially as the sentences get more complicated, to understand what those relationships are. So we can use this displacey method to draw this as a funky chart. So you can run displacey.render and pass in the document. The style of the render is a dependency chart. We put Jupyter equals true here so that it renders it inline. If we don't use Jupyter equals true, then the displacey will render a HTML or an SVG code rather than the pretty picture. Now, we can also set some options. So this is a sizing or a scaling parameter. So you can manipulate that and rerun it. And you could see what happens. Whoop, doesn't really work so well. So this is something that you might tune depending on the complexity of the sentence, the complexity of the chart, and the size of the space that you're working in. So the significance of this word Jupyter is that these collabs are essentially Jupyter notebooks, IPython, interactive Python notebooks that are running on virtual machines. And so you can use this if you're running this, these kinds of interactive Python notebooks locally, then you could still use this Jupyter command. So now that we have the visualization of it, it makes it a lot easier to see what the dependencies are. So we see that this saw verb, like in the chart here, has children Dan, Alfie, Day, and full stop. And so if we look, there's one of them, and then we have another here, Alfie, and Day is all the way over here, and there's a full stop dependency there too somewhere at the end. It also has a turtle dependency. Oh, okay, so Alfie has a dependency, a child of turtle. So there, Alfie has turtle as a child, and so on and so on. So it's a nice way of looking at how the words are related to each other. Let's say I change the sentence there. I'll put that Dan didn't see the turtle. I can change it fairly minor. A fairly minor change is going to change the dependency graph around. So I regenerate the table and then re-render the display, and we'll see that the verb is still the head of the entire sentence, but we've got more children or dependencies on the left side in this this phrase here, and the rest of it is still fairly similar. So for your assessment, play around with some different sentences, make up some maybe more complicated sentences, and let's see how those charts can get really quite detailed. Does anybody feel like dropping their chart into the Zoom chat so we can have a look? That'd be cool. So another technique that we can use is named entity recognition. So we talked about this in the lecture, that this is a process of labeling information in a sentence. And here we can use spaCy again to label words. One thing I should point out this is one of those little subtle things. You'll see that on some of these attributes have an underscore suffix. So spaCy works with hash values for things rather than text under the hood. So let's have a look at what happens if I take off an underscore. I should get a hash value there instead of a string. And so there we go. Get a nice big long number. So if I want the human readable form of a hashed attribute, I use the underscore suffix, and then I'll get that human readable value. So we'll see that down here as well. Where the label attribute has this hash, has the underscore. So we're using this so that we can see the human readable version of the label. Okay, so again, I'll pass in a sentence to the to Spacey, and it will create a doc generator. So we iterate through the entities in the doc and render them, see what we get. Now this is going straight to Spacey render rather than going to the table, because it's got this pretty cute visual kind of labeling interface. Now this, I don't know if you remember from the lecture, the output also identified Dan as a named entity. Let's see what happens. In the second example here, we've changed the name of that first person. We've still got Alfie the turtle, and we have a bit more information in there. University of Queensland Lake, another location, and maybe more common time information in the sentence. So 1 day. So to me, 1 day is time information, but evidently didn't occur enough in the training examples of Spacey to have been picked up as a label for a date time information. So whereas the first sentence only picked up Alfie as a named entity, the second example has a few. Ben has been identified as a person. Alfie has again been identified as an organisation. The University of Queensland Lake, and the lake itself has been grouped into that organisation, which is kind of interesting. Brisbane has been identified as a geographical position, and tomorrow has been picked up as a date. So this suggests that the name Dan didn't feature in the training data for this web small model. But I noticed something interesting, that if I prefix that with Mr. Dan, we might be able to encourage the recognition of that as a person's name. So that can be quite handy as well. So depending on the structure of the sentence, we'll get different results. All right, Lucinda's dropped an example in. Have a look at that. Okay. So there's a lot going on in this. And we have this great arc across the top, which is that a conjunction? Laugh, laugh. You're right. We should put some academic papers in here and see how these 200-word sentences might be represented in the dependency graph. Yeah, that's quite a sentence. The dependency labels that are used, I think I had a link to them. Oh, yep. So I'll back up in the dependency parsing information. I can open that link to see so these are all of the labels, the dependency labels. So we can click on these to see more information about the grammatical meaning behind the labels. So this can get into some pretty heavy linguistics. This is a bit beyond my capabilities, but it's good to know that the docs are there to read through if you need to. So there's quite a lot of options with examples. The identification of lake within the University of Queensland organisation is also quite interesting. So something that we could look at possibly is using the bigger model and seeing whether there are more examples in the large model that help the training or help the recognition. Okay, any other questions about that session? If not, we can look at some word vectors. Now, just before the start of the tutorial, I put Janet on the spot and asked if she would talk a little bit about the background to word vectors, the history of these things, and then we can look at how these are applied using the modern techniques. Might be nice to hear about the historical theories before we taint our concepts with such mundane things as practicalities.
Can I show a slide?
Yeah, sure.
Is that too technical?
No, you can. You ready? I'll stop sharing and you can take over.
Okay, sorry. Share screen. Okay, can you see the slide?
Yes.
So those of you who are awake, partially awake on Wednesday would have seen from words to concepts. And so, you know, Ben asked, what's a word vector? Technically, people would define it as it's a vector of numbers. So it's interesting that it's numbers, it's a vector, it's numbers, and it represents the meaning of a word, and I put meaning in quotes. Because as soon as you, as a computer scientist or AI researcher or NLP, as soon as someone talks about meaning, you should be asking, okay, this is a very fuzzy word, how are they going to cash it out? And there'll be multiple ways to cash it out. So that tells you there's going to be a lot of really interesting computer science underlying this phrase. So what we did in the discursus when we're going through discursus was look at how you go from a single word like Ventolin to a concept. And we had this vector of terms that co-occur with the word Ventolin. So asthma subscribed, Ventolin, puffer times day. And what I've done is add on the end a whole stack of other terms. So you might have, you know, 10,000 words in your vocab, 6 of them co-occur with Ventolin, and the other 10,000 minus 6 don't. So that's apple to zebra, and all of these are 0. So what you've got here is a vector of numbers. So this vector of numbers could represent the meaning of the word Ventolin. And then once you've got a vector, you can do all sorts of things with it. So this is just one way to create a vector of numbers. You can compress it. So instead of a 10,000 element vector, you could compress it down to 200 elements. You could select the most important words to choose, or you could create a subspace of that, a compressed subspace. So meaning can be cashed out in a couple of different ways. One is it can mean features. It could mean, and each feature means something, or it could mean micro features, where each feature contributes some evidence, but in itself is meaningless. So for example, a visual image, which might be a megapixel, each pixel contributes something, but each pixel alone doesn't really tell you anything. So each pixel in an image would be a million dimensional space, and each one would be microfeatures. So what's really interesting is usually not the individual numbers, but the relationships between those vectors. So it's the difference between two whole images that tells you something, not any, we can interpret one image, but it's usually the relationship between different word vectors that means something. So you can have, then the mathematics of how you do this is really interesting, because you can say, okay, if two words are similar, then they mean similar things. And then there's an entire mathematics. I had a student who spent 13-week project just studying all the different ways you can measure similarity in neural networks between different vectors. And there are hundreds of different ways of defining when things are similar, when things are different. You can look at things like Euclidean distances. You can look at cosine distances, so the angle between them. And those give you regions of space. But then you can also look at differences. So you could take a vector that represents boy and a vector that represents girl. And then if you want to know the difference, you could actually take, don't ask how similar they are, but ask what's the vector between those 2 points in space. And that gives you a difference between boy and girl. And then if you take something like a vector for king, and you apply the difference between boy and girl, so a king that's a girl would be A. And this is an analogy task. So then you'd say boy is to girl as king is to queen. So you can begin to ask what sorts of words might fit in that space. If you said boy is to girl as prince is to princess. So there's a whole mathematics of not just similarities between individual points, but similarities between relationships of points. That's probably enough on the how you generate them and how you measure them, but there's a whole beautiful mathematics around the shape of these regions and manifolds, surfaces. You don't necessarily want to use linear mathematics for these things, and that's where you get into things like deep neural networks, where each level is dividing up the regions and their relationships in different ways. Comments or questions?
The king-queen example reminds me of the doctor-nurse bias, that when, or was it, I think it was a Google system some years back, when you were searching for a female doctor, the answer was nurse.
Yeah.
Yeah, so the training data that these systems are trained on can really show bias that, if we're not careful, can seep through to the results as well. So that was something that was able to be corrected. Yeah.
If the bias is in the data, it'll show up in the word vector spaces. And sometimes it can show up and we didn't realize the implicit biases that were there. So quite often these can reveal things that are, we weren't even aware of ourselves.
The king-queen example in the collab that we'll look at now, I've got a link to an illustrated tutorial about Word2Vec, which is a particular library for working with word embeddings, word vectors. And this, I won't go through it in this session, but if you're interested in a bit more about that background and learn from images of things, then this is a really good tutorial where it shows this mapping. So the numbers that Janet had in the discursus slide here, and then looking at those numbers in multiple dimensions. So there's a 2-dimensional vector. What happens when we get to a 3-dimensional vector? We can still kind of represent 3-dimensional vectors in a 2-dimensional plane, but as we get build up many attributes of words, then the multidimensionality can become very difficult to draw. But so we can still list out those values, and then this tutorial has this really lovely representation of these as color bars, so replacing the numbers with particular colors, and then we can see these similarities of concepts across different terms. And so we can see that queen and woman are quite closely related in terms of the colors line up quite well. So this is a nice one to go through in your own time if you're interested. And there's a more detailed technical description at this link. So this will go through more of the architectures of how the word-to-vec models are trained. So again, this would probably be, there's enough juice in here to do a full lecture just about how word-to-vec architectures are. We'll cover similar sort of information in the NMT, the translation module coming up, so I won't go into the detail about that. But the first link in this collab, which I'll copy into the Zoom chat, is a link to an online visualizer, which just gets straight over all of the training and the maths and gives us a gorgeous data cloud that we can, how about that? Click on to explore the relationships between words. So we can see here that these words are clustered by their relationship, their similarity, so words that are close in meaning are close together. So we have Slovenia over there, we have legislation, economy, institutions. So we can see that within this data cloud that words cluster in meaningful ways. Now, Janet mentioned this collapsing of multidimensionality. PCA, principal component analysis, is one approach to doing that, and we'll use that in the prac in a moment. So there's some different techniques there that you can try with. You can play around with different data sets here as well. So this is a limited data set that's just a bit easier to see, but you could load up some other data sets that you can play with. And you could load up your own data set to experiment with in here. So it's really fabulous visualization, interactive. You can search, you can reduce data to really focus on, look down at particular points of interest. So there are a couple of links that were great to go through in your own time, depending on where your interests might be. So again, we'll use Spacey to look at similarities between words. So I'm in a new collab here. So again, I'll install Spacey with the upgrade. Now here's this message. So these packages will need to be, because of the upgrade, I'll need to restart. So I'll click restart runtime. This is why it's important to do all of your installations early, because restarting the runtime would possibly make any loaded files disappear, and they would need to be reloaded. I'll do that again just to be sure. Okay, requirement's already satisfied, so there's no need to reinstall that. I can clear this output just to clear up my screen. It doesn't remove the packages. Now, with this visualization, with the vector similarities, we're going to visualize them again. It's a lot easier to see this stuff rather than looking at pages full of numbers. And the corpus that we used in the first activity doesn't include vector data for the tokens. So we'll download and load this large corpus. So run this cell to do that. Nice bias image, Savita. Okay, that took a little bit longer to load, to download than the medium one, but now it's ready. So we get the message that we can load it, which we have done there. To begin with, we're just going to look at the similarities between these words. It's not really a sentence. Process a sequence of words using the Spacey model. Sentences tend to have a little bit more grammatical structure than 3 words in a row. So we'll run this and we'll see what we get. Now, we're making this Spacey document with the content. So we have an iterator, a generator that we iterate over, and we're going to iterate over each of the tokens in that document and look at the similarities between each of those tokens and the other tokens in the sequence. And so in our output, we're showing the text of the origin and the comparison, and we're using this similarity method here to very simply, very easily get the similarity value. So a similarity value of 1.0 that indicates that the words are highly similar and identical. Here, the similarity value of 0.8 in the vector space. These 2 words are very similar. Similarity value of 0.24 indicates that these 2 words, dog and banana, are not similar. So that's a very low value. So cat, dog, dog, cat. So dog, cat and cat, dog have the same vector value, the similarity value. So the vectors are the same both ways. Cat and banana. Interesting that cats are more similar to bananas than dogs are. So that shows us there's something about the training data that suggests that cats are more like bananas than dogs are. But cats are more like dogs than cats are like bananas. So again, play with these. We can have, what's the similarity of turtle and lake? Very low. Similarity of turtle and eel. Yeah, slightly higher. What's the similarity of all day fun? Okay, so we can compare words. We can also compare sentences. So again, we'll make 2 Spacey docs. That's the first one will be this sentence. And second So the first one's a line from Bowie song. Second is a statement. We're going to convert all of these docs into lists of tokens and show some information about the tokens. So the information that we're going to look at, does this token have a vector in the data, in the training data? What's the value, and is it out of vocabulary? So OOV is a symbol that we'll see occasionally in the course. This means that the token or the word that we're looking at is not included in the, or is not represented in the data. Then we will set up some columns again and show this information using the tabulate package. And we'll output a similarity value between the two sentences. So similarity of doc1 and doc2. And then we can also show the similarity of the first word in doc1 with a slice from doc2. So we can use these values to pick out individual words from the different inputs. So we'll run that and we get all of this information. So there's our text, our tokens. Now so again, we can see that these that word's been broken down into different token parts. So all of the words have token value, which is good. And then we see, sorry, all of the words have vector values, and then we can see what the vector is. And there's the OOV. So all of the words are covered in this data set. So that's good. Our comparison of the two sentences is 0.69. So surprisingly, it evaluates those two sentences as being quite similar. And the similarity value of the two words that we picked out, it's reasonable. So we can use these similarity information here to pick out or identify similar concepts or similar topics in the inputs. Now that's all well and good having these strings of numbers. Let's look at representing these in a more interactive form, that like what we looked at with that playground. So we're going to use this PCA package from sklearn library, and we'll use pandas as a data frame as a way of representing data in Python quite easily. Here's our input. Rather than starting with a sentence, we'll just have a list of words, and we're going to create this vector, get the vectors for these words. So we'll be getting vector information for each of the words in this sequence, this list. We'll collapse that down to our 3 axes, and then we'll represent these in a data frame. So let's look at that first, and then we'll plot those in a visualization. Okay, so cat, kitten, dog, puppy, and shoe. And my expectation is that the first 4 of these are going to be fairly similar in space, and the last one will be an outlier. And it looks like it in terms of the numbers. So on the x-axis, shoe is appearing to be well away from the other values, seem to be kind of clustered in around between -1.3 and 2.14. And the y values there within a pretty close range. The y value here is quite low. And the z's also, there's a kind of clustering of these, whereas the z-axis value of shoe is quite low. So again, you could look at that and have a kind of intuitive feeling for the relationships, but there's nothing quite like seeing a visualization of it. So we can use Plotly to create or plot a 3D scatter chart with the data on the different axes, and we can label the dots with those words. So the vectors between cat and kitten are, there's a similar relationship there to as the vector from dog to puppy. So like the vector in between cat and kitten here is the same or similar to this vector between dog and puppy. So we get an idea that there's a kind of relationship between those two things, similar relationship. Especially, I'll try not to turn the graph chart upside down. And likewise, the distance between kitten and puppy is quite similar to the distance between cat and dog. So we can have an understanding, depending on which way we're kind of reading the data, we can interpret different things about the relationships between those entities. But whichever way we read about those cat, kitten, puppy, and dog, the shoe thing is kind of way out there on its own. So we get a very clear sense from the visualization that these four are quite similar and shoe is quite different. So again, this is a nice activity to try with your own words. So try putting different words up here. Feel free to add more. Let's see what happens if I do some good old turtle, lake, eel. Maybe I'll put shoe in there as well. Okay, I'll run that. Rebuild the data frame. And again, I can see that there's going to be a difference here, and then I'll rerun the plot. Oh, they're much more evenly distributed. What if we were to put astronaut? Okay, so that's really changed the shape of the chart quite a bit. So for some reason, astronaut's more similar to lake on that dimension than shoe. So again, a fun thing to play around with. And the scatter plot gives us a good way to kind of represent these concepts. Okay, so that's using Spacie. Another approach is to use a package called, or a library called Word2Vec. And we'll use NLTK and the GenSim distribution of Word2Vec for this. So here we'll download a data set. So ABC, whoops, my Colab just disconnected, so I'll reconnect. It's like my internet's getting a bit flaky. 1 moment. Try this again. Okay, so internet stabilized again. I can proceed. Importing NLTK, importing GenSim, download the ABC dataset, and download the punctuation dataset. So the punctuation dataset is used to tokenize. And we're using the magic keyword time to see how long it took. So that was only a few milliseconds. Felt like an eternity when the internet was unstable. So now we'll use the sentences from the NLTK ABC corpus, so which we can access with this notation, to train the word-to-vec model. So we can run this. This will retrain, this will train word-to-vec based on this corpus, and we'll have access to that in the ABC model. Now we can use, like Spacey had that similarity method. Here we can use the wv.mostSimilar and pass in a word, and we can get a list of similar words, the 10 most similar words to the import word. So that will give us this list and a similarity value. So words, the 10 most similar words to banana, some surprises in there. Citrus, I'd expect, maybe. I'm surprised that fruit is not in the top 10. It's kind of odd that chicken's there. It's very surprising that representatives features quite highly in this list. So there's something about this data source that maybe doesn't have many examples of banana, or maybe doesn't have many examples of bananas in recipes or something. So we can see that the information that we work with is very dependent on the data, the biases in the data. Yeah, a lot of these, so Lucinda has just put in a comment in the chat that it looks like the examples might have something to do with agricultural or trade documents. And particularly if the data sources are scraped off the web, they often have, there's a lot of news information. Whereas if we were training this with say a Twitter corpus, there might be much more conversational kind of responses. So it's something to consider when you're building a system. Choose your data carefully. So we can look at the similarity between banana and citrus, and we're expecting that, well, that's one that we saw before. And here's a similarity. What if we did that with something else? We'll see if boat is in there. So rerun that. I probably should have put these into a separate code cell so that it didn't have to retrain the model every time I wanted to try some different similarity values. So let's do that. This is sort of, I'll just clear that output. So I'll leave the trained model there. I'll make a new code cell, and this put the content, or put the quicker running stuff in here. So now I can play around with that without having to retrain the model every time. So the similarity, so banana and boat do rate pretty highly. That's interesting. What about banana and dirt? Or what about tree? I would think that would be pretty high too. Yeah, okay. So there's our value for banana and boat. There's our low value for the banana and the word nobody, and the value for banana and tree. Okay, so this is how we use word2vec. We can train that on custom data. So in this example, we used the ABC corpus. We can train it with our own data by first importing a tokenize from NLTK. You could use one of the other tokenizer, or you could write your own tokenizer, but we might as well use the handy features of NLTK. There's so my corpus here is this text. So it's just a few sentences. 2 times a day I walk to the shop. The shop owner says hello both times. The turtles are in the lake. The turtles are in the shop. The shop is open. The turtles are in the shop. How did the turtles get in the shop? To some nonsense. But we tokenize that to make a corpus, our training corpus. So I'll run that and we'll see the shape of this corpus. So it's a list of sentences. So this is the format to begin with, and then we'll tokenize each of those sentences. So we should end up with one master list containing individual lists of tokens. So you might remember this from the data processing collab. We can use NLTK's word tokenize, and lo and behold, like magic, I get my my big list that contains individual lists of tokens. Funnily enough, I've got a repetition in there. Okay, so now we can use that tokens corpus to train Word2Vec. We'll do that. The other, when we're working with a toy corpus, this is important to pass in this parameter, a minimum count. Typically, Word2Vec will ignore any data that doesn't have less than 5 instances. And in a toy corpus, the only word that I think would have less than 5 is the word the, but that would be excluded anyway because it's a stop word. So if we pass in min count, then at least all of the non-stop words will be recognized or trained upon. So press play happens instantly because it's a tiny corpus. So if you were working with a larger corpus, that might take a little bit longer, but probably not too long because it's just text. And then we can look at some similarities. So with our toy corpus, what's the similarity between the words turtles and lake? It's extremely low. What's the similarity between turtles and shop? That's slightly higher. What's the similarity between shop and lake? That's quite low as well. So we have very few examples of recurrence of instances in the corpus. So this is why the values are so low. But why do you think turtles and shop rates higher than turtles and lake? So put your thoughts into the chat while we continue. Now we can also demonstrate what happens if if we look for a similarity of a word that isn't in the corpus. And we can do that by just requesting the vector information for a particular word. And if that fails, then we get this message. So we start to get a sense that the model only works for words that it was trained upon. And like Hunter has answered in the chat, the significance or the similarity is based on the instances in the sentences, not conceptually. So Word2Vec learns from the instances of contexts in the training data that you give it. It doesn't have any innate understanding of language. So you can use Word2Vec to train other languages. So Word2Vec doesn't necessarily know about English or Korean or other languages. It really needs to, it only learns from the data that you train it upon. So this is demonstrated here by having this unexpected higher similarity for non-related concepts from a general English point of view, unless perhaps if you worked in an aquarium or a turtle shop, then you probably would have a higher correlation between these words than if you worked at the University of Queensland. Okay, how did that go? Does everybody proceed through that collab happily? So the last activity is to look at sentiment analysis. And here's the link in the chat. So again, open this up and save a copy into your Google Drive so that you can work on it, generate the assessment responses, and play around with the different information. So this is a collab which has come from an online repository of various notebooks. So the link is in the collab. There's some really nice NLP activities in there if you feel like playing around with some more techniques. Now, in this session, we'll use NLTK and another matplotlib for the charting, pandas again for the data framing, and we'll use this text blob package as well. So we'll begin by installing all of these things. These all installed happily for me because I ran this fairly recently. And we're going to download three corpora. This lexicon, data set of movie reviews, and our good old punctuation corpus. So this might take a little while for you. You can see that performing the sentiment analysis using NLTK's built-in technique happens very simply using the sentiment intensity analyzer. So there's our input sentence. This restaurant was great. We'll run this code cell and we'll get some ideas about the emotions, the sentiment in this utterance, in this sentence. So below the code cell, we have some description about what the data here is telling us. Is it negative? What's the negativity, the negative sentiment, the neutrality, positivity, and then the aggregated value. So what's the aggregation of those values, negative, neutral, and positive, and the compound is our sort of sum. So let's have a look at some other examples. Sentiment. That's kind of surprisingly neutral. And this is an interesting adaptation of the input sentence. If we add a little smiley face there, then we increase the positivity value. Or I might even try, I wonder if a bigger smile might even boost that up a bit. Yeah, so we can influence the sentiment analysis through the inclusion of things like emojis, emoticons, sorry, so NLTK maybe doesn't recognize emojis. And there we go. So the description underneath it tells us that this Veda model doesn't understand emojis, so it won't sway the sentiment in the same way that it does with the emoticons. Okay, here's another approach. This is using text blob, and we'll compare the sentiment using text blob versus the NLTK one. So I'll install these, import these packages and run it. And there we get our information. So the polarity and the subjectivity. So it's slightly different information that it's giving us, but again, it's a very easy way to get sentiment from the system. We can try another analyzer. So we can specify a particular analyzer, run it again. And so now we can see we have a separated positivity and separated negativity. So the different analyzers, the different models will give us different format values. So this is important to know when we're using these in other tool chains. So there's a bit more information there about how these values are derived. I'll leave that for you to go through in your own time. The fundamental thing is to know that the training data is significant, has a significant influence on whether these sentiments are, or how these sentiments are detected. So this Colab has some example sentences that we can put into a data frame. Some of these are going to be clearly positive, some of these should be clearly negative, and we can run these and make like a leaderboard style output of the results using these 3 different classification systems. So text blob, the Bayesian one, and the NLTK one, and we can see that they only occasionally agree. So this is kind of valuable to see that different sentiment analyzers can have very different understandings of the sentence. So like NLTK is evidently picked up on this repetition of the word love, and it probably also thinks the word kitten is kind of cute, so that might rate positivity value of the word kitten might be quite high. Where there's, so this, I'm not sure how I feel about toast, is across the board, that's a fairly neutral analysis from the 3 different systems. And this chirping birds irritating sentence is also scored quite low across the 3 different systems. Something that's worth knowing is that these negative values in the sentiment analyzers, a negative doesn't always correspond with a poor value. So we'll see in a moment that we can have a minus 0.8. Sometimes that can be a deviation from 0 in a particular direction because it's a vector. It's not necessarily a negative value, doesn't always mean a negative sentiment. It can be a negative vector in a different dimension. Okay, so something to think about. One of the takeaways about this, and we touched on this in the lecture, was the traps of sentiment analysis, particularly these concepts of sarcasm, negation, and ambiguity. So sarcasm is a particularly important one to consider, where natural languages have, there's a very poor ability for a computer to detect sarcasm just through the words itself. So we've got a Colab here that we can work through to train up a system that is a sarcasm recognizer. That's been trained on a data set where the data has labeled with \S tags indicating sarcasm from a scrape of Reddit website. So there's a link there to an article about traps of sentiment analysis. So talking about sarcasm detection, some examples. Hey, this looks like a perfect plan. I love being ignored. Like those guys believe a word they say. So you can see that the construction of the syntax of the sentence sometimes belies the underlying meaning. Very helpful indeed. Now this is an utterance which could be interpreted in a highly positive way or in a very sarcastic way. There's some good links there to papers which specifically looking at sarcasm through the negation or the mismatch between expected numerical values in utterances. So that's probably more than we will go into in this tutorial. We can take this session out with a quick run through with the sarcasm detector. So there's nothing in here for assessment. This is more just for interest's sake and a first experience of using TensorFlow in the Colab. So we'll put that link in the Zoom chat for this Colab. This will train a sarcasm detector using a corpus of utterances scraped from Reddit that have a particular /tag in them. If you wanted to try this with a different data set, there's a link here as well to a large annotated corpus. Oh no, sorry, this Colab will use this small corpus just so that we can train it more quickly. But if you wanted to use it with the large corpus, that the link there, the 1.3 million data points. Okay, so again, we'll import all of the packages that we need. And here, so we're going to start using TensorFlow. So one of the great things about Colabs is that TensorFlow machine learning framework is built in, so pre-installed, and so it's quite easy to get up and running. So we'll install all of those requirements, and then we'll download this data set, and we'll have a peek at the first couple of elements in that data set. So this data set that we're working with today is a web scrape of a whole bunch of news articles. And some of I don't know if you know The Onion, some of the news articles are likely to be truthful. Some of them may be false, but still non-sarcastic. And some of them will be sarcastic, particularly these articles from the website The Onion, notorious for their sarcasm. So here's a quick look at The Onion. Mum is starting to fear her son's web series and the closest things that she will have to grandchildren. You can see lots of sarcasm on The Onion. Okay, so we've output the first 1,000 characters just to get a sense of the shape of this data set. So it's a list of objects with a link, a headline, and a is sarcastic value. We'll put that into, we'll make a data frame that has some sentences, and which will just be some slices of these headlines. And the label, is it sarcastic or not? So here are some of our sarcastic headlines. And now for training this system, we first need to split the data set up into a testing and training set. We'll do that computationally. So we'll do what's this one? It's a a 75% split. And we set some properties for the training, and then we'll tokenize the data set. We'll go into more detail into different TensorFlow tokenizers in the NMT lecture coming up. And something that we need to do is to pad out sequences. So if some of the sequences are shorter than others, then we'll need to pad them so that they're the same lengths. This will help with the creation of the vectors. And then we're ready to, did I run that? Okay, then we set some parameters for the architecture. And then we're ready to train it. So we make our NumPy array. We can set the number of epochs. So if you want to get through this in a hurry, you might lower that. It's still not going to take too long because it's only a small data set. So the epochs are the number of iterations that the training will take, and it shows us we'll have some accuracy values here. The accuracy and the loss, we'll see those change as it goes through the training process. Yeah, so Hunter has put a note in the chat. One problem of using sarcasm detector is that if you're looking for it, any sentence that could be used sarcastically will be classified as sarcastic, even if that's not the intent. And once we've trained this model, we can put some sentences, we can test this with our own sentences and get the prediction, and you'll see some of the results might be unexpected as well. Sarcasm is context and culturally specific, depends on who you're speaking to and whom in what situation, says Janet. So we've trained that system. It's reached the 30th epoch, so it's done good there. Now I can put some sentences in here and we'll get some responses as to whether this system thinks these sentences are sarcastic or not. So my first example, sick car mate. Second, you look surprisingly good today. And the third is a news headline from today about care packages being sent to work in our community. So let's run that and we'll see what this model thinks. Now, the model thinks the first two sentences are highly sarcastic and that the third is not sarcastic. So this is, you look surprisingly good today, has been identified as sarcasm, which is kind of funny because a literal reading of that would be that it's not, there's no indication from a literal reading that that would be sarcastic. So see how you go with your own sentences and see if you can come up with some sentences that are highly sarcastic or that are predicted as being highly sarcastic. It's kind of fun to try putting in sentences that you expect to be neutral or even positive and non-sarcastic to see that a system can classify these as being highly sarcastic. Again, it depends heavily on the training data. So if we were to swap out that training data in this model with the Reddit corpus or maybe a Twitter corpus and see how the same sentence might be classified in different ways based on the training data. Now, I would expect the Reddit corpus is going to be, there's a high degree of sarcasm in Reddit, and so I would expect that it would be more accurate at detecting sarcasm than this headline corpus. So the headline corpus is quite limited in terms of like the sarcasm that it's learning from is maybe only from one or two sources. So there's the social and cultural context of the training data would be seen through those as well. Okay, I think that's taken us through our collabs. If you're interested in playing more with these sorts of tools, then there's days worth of fun at this URL. I'll put that into the chat. The super duper NLP repo, and I think at last count there's, oh, there we go, 339 collabs, a range of techniques from text processing through to speech recognition. Remember from the lecture that speech recognition, speech generation, text to speech are all considered NLP in a very broad sense. And there's a range of different architectures here, different models that you can use. So we see there's Word2Vec that we've used today. TensorFlow frameworks will be there. More spacey things, more named entity recognition. So if you want to go further into any of these techniques, then this is a good place to start of identifying the task that you're interested in and then going through the collab. These are all contributed from the, these are open source community contributions, so the quality of the documentation will vary. But I might put up some of the better ones onto the Voyages site for further work. Okay,